In a servo-hydraulic system with a constant supply pressure and a one-to-one valve, a single rod cylinder extends faster than it retracts. We will present the formulas for the velocity of a cylinder in both directions, then explain with detailed algebra how these were derived. These formulas use the following symbols: PS for supply pressure, kV for the valve constant, which is a number that defines how much flow will occur at a given pressure differential. We are focusing on a one-to-one valve which has equal flow in each direction. AA is the area of the A side of the piston, and R is the ratio of the area of the A side of the piston to the area of the B side of the piston. The extending velocity is given here, and the retracting velocity here. The only difference in these formulas is R in the denominator inside the square root. That means the retracting velocity is the extending velocity times the square root of 1 over R. For example, for a ratio of 2, meaning the A area is twice the B area, the retracting velocity is the extending velocity times 0.707. To derive these formulas, we first consider constant velocity. Constant velocity means there is no change in velocity, and therefore the acceleration is 0. Newton's second law says that force is equal to mass times acceleration. So, if acceleration is 0, the force is 0. Therefore, at constant velocity, the net force on the piston must be 0, meaning force A and force B are opposite and equal. We will neglect friction for simplicity. For a cylinder with motion seals, friction is usually relatively small, maybe around 1% of the maximum force. Starting with FA equals FB, we will analyze the pressures, flows, and forces to determine the formula for velocity. One of the main concepts in these formulas is the pressure drop as oil flows through an orifice. For a valve, it is equal to flow divided by the valve constant squared. As flow through an orifice increases, the pressure drop increases, not linearly, but by the square. Now we will start with the main formulas. First, for the A side of the cylinder, for a given flow QA, the pressure drop from supply pressure to the cylinder pressure is given by equation 1. Supply pressure minus pressure A equals flow A divided by kV squared. For the B side of the cylinder, for a given flow QB, the pressure drop from the cylinder pressure to tank is given by equation 2. Pressure B minus pressure tank equals QB divided by the valve constant squared. The A-port flow QA is calculated simply as velocity times area A. And the same for the B-port flow, velocity times area B. From Newton's law, at constant velocity, force A equals force B, which leads to equation 5. Force A minus force B equals 0. Because force is equal to pressure times area, equation 5 becomes equation 6. PA times AA minus PB times AB equals 0. Restating equation 6 here, we will work on substituting PA and PB. For PA, we go back to equation 1 and rearrange it to equation 7. Pressure A equals supply pressure minus the A flow divided by the valve constant squared. And we substitute QA with velocity times area A to generate equation 8. Pressure A equals supply pressure minus velocity times area divided by the valve constant squared. For PB, we do the same. Back to equation 2. Since pressure tank is equal to 0, it becomes pressure B equals flow B divided by valve constant squared. Substitute QB with velocity times area B, and equation 9 becomes pressure B equals velocity times area B divided by the valve constant squared. Now, back to equation 6, we substitute PA and PB from equations 8 and 10, and it becomes equation 11. Let's review what we did so far. We started with force A minus force B equals 0. We substituted the A and B forces with pressure times area. Then we substituted both pressure A and B with the pressure drop formulas that included velocity times area divided by the valve constant squared. Now, multiplying area A with both terms in the parentheses gives us an intermediate equation. Moving the rightmost terms to the other side gives equation 12. Multiplying the area A's and area B's together give this, with the area A's and area B's cubed. And consolidating V over KV squared gives equation 13. Restating equation 13, we see the equation is in a form where we can fairly easily solve it for velocity. But first we introduce R, which is the ratio of the area A to the area B. So area B equals the area A divided by R. We substitute for area B to get equation 14. Now area A can be pulled out of the parentheses, which simplifies the equation to 15. And we divide both sides by area A, giving equation 16. Now we rearrange a bit, isolating V over KV squared, then move KV squared to the other side, so we are left with V squared. Taking the square root of V finally gives the equation for the velocity of the cylinder while extending. The formula is fairly straightforward. It has a valve constant, area A, supply pressure, and the ratio of piston areas. For the retracting velocity, it is almost the same. We start with the basic equations. From the pressure drop on the B side, we get supply pressure minus pressure B equals QB over valve constant squared. From the pressure drop on the A side, we get pressure A minus pressure tank is equal to QA divided by the valve constant squared. Then the basic flow equations. Flow A equals velocity times area A. Flow B equals velocity times area B. Recall equation 5. Force A minus force B equals 0. And equation 6, where the forces are substituted with pressure times area. Now we find pressure A and pressure B again. From equation 20, we rearrange to get 24. Pressure B equals supply pressure minus flow B divided by the valve constant squared. And substituting the flow with velocity times area gives equation 25. Same for pressure A. Pressure tank is 0, so it becomes pressure A is equal to velocity times area A divided by the valve constant squared. Now we substitute pressure A and pressure B into equation 6, giving equation 28. So let's take stock again. We started with force A minus force B equals 0, substituted the forces with pressure times area. Then we substituted pressure A and B with a pressure drop formula using velocity times area divided by the valve constant squared. Rearranging gives 29. We are not done yet, but let's compare the equation at this stage to the same equation for the extending case. Notice the right-hand sides are identical. The only difference is the area A and area B on the left-hand side. Because the area A is larger, the left-hand side of the extending equation must be larger than for the retracting equation. Since all the other variables are fixed except for velocity, we can deduce that the velocity for the extending case must also be larger than the velocity for retracting. We will continue developing the equation so we can tell how much larger the extending velocity is. Collecting terms from equation 29 gives the equation with area A cubed and area B cubed. Again, we substitute area B with area A divided by R to give equation 31. Now we start solving for V by pulling out area A cubed, then dividing both sides by area A to get equation 33. From equation 33, we isolate V over KV squared, then multiply by the valve constant squared, then take the square root, and we have the retracting velocity. So here are the equations for extending and retracting velocity. The only difference is R in the denominator of the square root for the retract velocity. Therefore, the ratio of retracting velocity to extending velocity is the square root of 1 over R. This is not a simple linear ratio of the areas on each side of the piston. As explained earlier, for a cylinder where area A is twice the area B, the ratio is 2, and the retract velocity is 0.707 times the extending velocity. With these formulas, we can also look at how system pressure affects velocity. System pressure is inside the square root. That means that if the system pressure is doubled, the velocity increases by the square root of 2, which equals 1.414. This information should help you better understand the workings of a servo-hydraulic motion system so that you can design a system that meets your requirements. For more information on hydraulic system design, see Delta Motion's other videos and go to deltamotion.com to request your free hydraulic design guide.